Hello, this is Math 2231 coming to you from the College of DuPage for the summer of 2020, and this is the conclusion of a lecture called New Limits from Old, and it's Old Algebra and Trigonometry. We're going to start by proving two spatial trigonometric limits. This is the first one, and this is the second one. Let's start with proving this one. We're going to use a geometric argument. To avoid confusion of different uses of x, the proof is presented using the variable theta. That's a dummy variable, and we're going to let theta be an acute positive angle measured in radians. So we're going to be talking about the limit as theta goes to 0 of sine theta over theta. So that's how we're going to start. Now, this is a picture of the unit circle. Several things I should mention. The center of this is 0, 0, and the radius is 1. So any point on the circle, the distance from 0, 0 is 1. And you know from your trigonometry that any point on the unit circle has x squared plus y squared is equal to 1. And you know from your trigonometry that the x on the unit circle is then given by cosine of theta, and the y is given by sine of theta. Now, there are three geometric figures that we're going to look at. The first is this smallest triangle right here. And again, we're letting theta be approaching 0 from the right. So that means this is a tiny angle. It certainly is acute in this case. So we're going to be able to use some right triangle trigonometry. So this small triangle that goes from 0, 0 to cosine theta, sine theta down to 1, 0 is this picture over here. Now, we have to use the formula for the area of a triangle, so it's going to be 1/2 the base times the height. Well, to find the height, you take the perpendicular to the base. So this length from here to here is 1, but the height is sine theta, as we talked about over here. So the area of that is 1/2 sine theta, or sine theta over 2. There's a big triangle here as well, and here is the big triangle. So you start here, 0, 0, you go up to 1. I'm going to convince you that that is tan theta, and you go down to this. Well, you see in this one, going from here out to here is 1, and the tangent is the opposite over the adjacent. So you see the tangent of theta is going to be the height of this, because the tan theta over 1 is the y over 1 is the tangent of theta. So the y is the tangent of theta. So the area of this triangle is going to be 1/2 the base, but you see this is perpendicular already, because you see this x coordinate was 1 and that x coordinate was 1, so that means that is perpendicular. And so 1/2 base times the height ends up being 1/2, and the height 1/2 of 1, and then the height is tan theta. So you see that is the area of that triangle, and that triangle is clearly bigger than the other one. And caught in the middle is the area of the circular sector. Now that's this circular piece of pie. It's a radius of 1 here, it's a radius of 1 here, but here we go along the curved angle, and you can tell from the picture that this area of this sector is between the two. And you remember, if theta is in radians, the area of the sector is 1/2 theta times r squared. But r is 1, so this is theta over 2. Now, if we multiply all the way through this inequality by 2 over sine theta, and we're in the first quadrant, so that means sine theta is positive, so we preserve the sense of the inequalities, and we simplify, and we realize that the tangent is the sine theta over the cosine theta. And we multiply all the way through by that, and this is the resulting thing that we get. Now the 2's will all cancel, and this is the expression we get. And if we take the reciprocals, that will reverse the sense of the inequalities, and so we have this. But now you see we're ready to provide the end of this part of the proof, because you see this expression is caught in between this one and this one. So the limit of this, you just plug it in, as theta goes to 0, that becomes 1. The limit of this, as theta goes to 0, becomes 1. So the limit of this has to exist and become 1. Now, because the cosine of theta is the same as cosine minus theta, and the sine of theta over theta is, you put minus theta there, you can conclude that that also is true if we approach theta from a negative direction. So you can apply the squeeze theorem, and we conclude that the limit as theta goes to 0 of sine theta over theta is equal to 1. This is something you should commit to memory. Let's go to the other one, and you actually should be able to do this one. Let's see, you know what to do. Let's see how you did. Well, we're going to just use algebra, and we're going to multiply top and bottom by 1 in a clever way. So we'll take the algebraic expression that we have, and we're going to multiply top and bottom by the conjugate. Now, you see, we know that this is a minus b times a plus b, so this is going to be a squared, 1 squared minus b squared, which is the cosine squared. But we know that this 1 minus the cosine squared x is the sine squared x from our trig. So we have this, and again we have this factor that's in the denominator still. Now I just reorganize this. I'll put one of the sine x's here, the other sine x here. I'll take my x and put it here, and I'll put my other factor here. And now I can talk about taking the limits, because the limit of this thing is the same as the limit of this thing. So the limit as x goes to 0 of 1 minus cosine x over x is the same as the product of the limits. This limit we just learned was 1. This limit we can just plug it in and we get 0, so the answer is 0, and we have proven that theorem. Okay, here's a problem for you. Find the limit as x goes to 0 of 10x over x. You know what to do. Let's see how you did. Okay, well, the limit as x tends to 0 of tangent x over x is, you see the tangent of x is the sine of x over the cosine of x. And there's my x, so I reorganize it this way. The limit of the product is the product of the limits, so this is 1. This is a just plug it in limit. That is also 1, so 1 times 1 is 1. Here's another problem. Find the limit as x goes to 0 of sine 4x over x. Let's see how you do. In fact, now let's see how you did. Well, you have to change variables here basically, because this is not exactly what you want. But now we use that math technique of multiplying by 1 in a clever way. So I multiply by 4 over 4, but then I jerk this 4 through the limit sign using my properties of the limits. So now I observe that this is let y equal 4x, and when x goes to 0, 4x is going to go to 0. And so I have 4 times, these are dummy variables, here's the change of variable, and I get 4 times 1, or 4 is the answer to this problem. Here's some true-false exercises. If it's false, explain why and give an example that shows it's false, or explain why it's false, I guess you should say. Okay, you know what to do. Let's see how you did. Okay, the first one is false because the limit from the left is minus 1, the limit from right is 1, the limit does not exist. 18 is false because this is a just plug it in. That's not 0, that is pi, and the answer is 0. 119 is true because the limit doesn't depend on what happens when x is equal to 0. It has everything to do with what happens near 0. Number 120 is the limit does not depend on what f does at c. That's false. Let's see, this one, number 121, is false. The left limit was 3, the right limit is 0, the limit does not exist. And for 120 true, notice that it does make a difference. This would be true if this were less than or equal to. And here's an example of red and blue functions that sort of tell you do have to think about what happens whenever in the limit. And you see that it does change, that you end up with a less than or equal to. Oh, wow, here's an embedded quiz. This is going to be posted on June 8th, and whenever I post it and send you the email, there's a 24-hour fuse to complete this. It will go away after that. It's worth 10 points. Take-home protocols apply, and you're supposed to evaluate this expression down here or explain why the limit does not exist. We just put it here. The answer must be entered in the Blackboard assessment answer sheet within 24 hours of posting the lecture in Blackboard. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless.